So the less we pay attention, the smaller the memory can be condensed. If we're not really, we're bored, time's going slowly, so this is relating to that kind of paradox, that very temporally dense moments where there's lots of stuff going on. While you're in it, seems to go fast. In retrospect, seems to go slow. If you have a large period of open time, it seems to go very slow while you're in it, but in retrospect, it seems to go very fast because you've condensed it because you don't have many points of change in there. And so it condenses down to smaller, and you have less accuracy in your memory of what was going on during that time. So the closer the compression or the scaling factor is to 1, the more accurate your information retention would be. Okay, I think we've probably covered all this. Yeah. Okay, so Grobel says that smallest bit of the fractal is where timelessness comes in because it can't be subdivided anymore. I suggest that it's the pattern itself that is timeless, in that time emerges from timelessness, and that this moment that we're experiencing right now is a chunk of timelessness, and that we store time in our memories as condensed memories within this timeless moment. And so this moment is this axis of timelessness from which time is continually unfurling and deepening into. So the largest pattern, if we're using the Koch curve as an example, that line with the triangle in it, that can be thought of as the moment. And then when you remember that moment, store it as a memory, you're shrinking it down, storing it in a couple different places in your brain. And also the larger process of time is storing this present moment in multiple brains, in multiple perceiving subjects. And so there's that idea again of the more repetitions of something you can get, the more accuracy is going to be preserved. The more perceiving subjects are experiencing a moment, they're all going to have different memories. Their rate of they're going to compress that experience into different things depending upon what they've paid attention to. But the sum of those experiences is going to be closer to the actual experience than any one of the individual experiences. Okay, and so the idea is that this present moment is timeless, and it is time is deepening into this moment as we're storing and retaining the information. And so I think it's not the indivisibility that makes the prime timeless. I think it's the universality of the pattern, the prime, that it occurs at every level of scale that makes it timeless. Okay, so then we can look and say, all right, well, how does timelessness show up in reality? Where does it really exist? So, we have a general idea of this moment is timeless. The past and the present is existing here, but only in an abstract way. So one place it shows up is in light-like curves, or with photons. So this is a light cone. So this is here and now. This is the future, that's the past, and this is space. All right, so this is a map of a photon in space. So all of the boundaries of the upward cone and the downward cone are the places that photons can come from and can go to, because this slope right here is the speed of light. All right, so inside the curve, we'll just talk about this one's the light curve. For photons, there is no time. They exist outside of timelessness because there's no space-time separation on these paths. And maybe we'll just leave it at that for right now, since we're moving along here. Okay, so we talked about Penrose's timelessness, his idea of insight being that aha moment, getting the gestalt, stepping outside of time and being able to recognize those patterns that occur in time. And I talked about how they both use Gödel's theorem, or Penrose and Natal both use it, and they see things that are true and undemonstratable, unprovable with algorithms in both quantum mechanics and fractals. And so for Penrose, he takes that to be, okay, well, consciousness has these moments of insight, and so it must be utilizing some mechanism in nature to access this timeless realm, and it must be a mechanism that is not computable. He's looking for non-computable algorithms. And time's kind of running out, so we'll just say, okay, so the Mandelbrot...
Go over a little bit.
Okay, okay. So the Mandelbrot set is... I'll bring up a little visual while I'm talking about... Well, I'll do this first. Okay, so the Mandelbrot set is actually the black portions of these, and what's happening here is this is the, a zoomed out version, and then they're zooming in on this square, and it's giving us this image, and then they zoom in on that little zipper part even more, and we get this image, and we zoom in here, and we get this image. I'll bring up a motivation, or a video that will show it a little bit better. But so this set is generated by, oh, I lost my C1 over there, and that's inaccurate. So it's generated by a very simple algorithm. You start with one point on the complex plane, so this is imaginary numbers going that way, so the square root of -1 is an imaginary number. And you pick a point, and you square it, and you add it to itself, and then it puts out your new constant, which you square and add it to itself. And what you're trying to figure out is by following this algorithm, it's going to bounce around and it's going to go to another point, and that constant you square and add to itself, blah, blah, blah. And is it going to escape a certain radius, or is it going to be stuck in that radius? And so all the colored portions are points that escape that radius. And the black portions are ones that we think don't escape the radius, but we can never be sure, because it would take an infinite number of iterations of that equation to tell for sure if it really didn't ever escape. And so the Mandelbrot set is most complex on the boundary between those black regions and the colored regions, because that's where if you zoom in, you're like, okay, this point's going to be not escape and this one's going to escape, and you try to get it real accurate, and no, you can't really tell. You can never tell where the boundary actually is, because the closer you zoom in, the more complex it gets. Infinitely more complex. So let me see if I can bring up that video for us. It's got some music to go with it. And so this would be, this is zooming in on a fractal. This is kind of similar to the mechanism of remembering. So we had that big, bulbous shape, and here it is again, condensed, smaller, and repeated. And it's just going to zoom in on that boundary line between the bounded point, or the bounded points and the unbounded points, trying to determine which is which, and it just continues to find. And this is an example of a space filling curve of fractal dimension 2. And so the way fractals interface, because this has all been within a finite space. This is traversing the dimension of scale. So the way fractals relate finiteness to infinity via scale, I think is definitely analogous to how timelessness and time relate.